random nut screws and bolts. What's going on, man?
I have no idea. Isaiah took it last time.
No, Isaiah's fault to keep track of this stuff.
Look, I'm not getting paid to keep these organized.
This is exactly what
No,
I'm paying
it's
you to
not
do.
my
This is
responsibility.
ridiculous.
No.
Pause. Has this ever happened to you in your work life? Well, this is a common problem in workplaces. So to solve this problem, we present to you our capstone project, Rack-A-Jack. Our presentation is broken up into 7 key parts. We're going to address the problem that we are facing, the solution of how we want our solution to look, the motion at which we plan our robotic system, the robot controller that we designed to control it, the database at which we designed to keep track of all the parts in their stock, the robot itself and its functionality, and the storage and manipulation of the parts within our system.
So in the manufacturing process of trucks and Edison motors, workers usually find themselves making unnecessary trips to part shops in order to fetch parts. And it's because they're not keeping track of the inventory. And in addition to that, there's sometimes waste time looking through disorganized parts. So we came up with a plan to solve these problems by keeping everything organized and also keep track of the stock. Based on our plan, the user will order and receive the parts by just interfacing with a very simple program. Once the order is placed, the program will start to verify the order. If the part is being used by someone else or it's not available, then it will notify the user. Once the order is verified, then the system will start to plan the motion of the robot, and then after it's done, it will send all the data to the robotic system to execute the motion.
Now, the motion of our robot has been described with the vector interpolation algorithm. By controlling the angle of a vector, the magnitude of the vector, and the height of the vector, we keep track of all the points that the vector goes between its start and its endpoint. All of this complexity that we designed in the control of our software has been compressed into one function call, where we give it the start, the end, and if we want to do a linear trajectory or we want to do a circular one around an object. To describe the displacement of these key features, we designed our own 4th order polynomial system to efficiently maximize jerk, so we never overstress our machinery, and to allow the robot to move faster than what it would take for a normal human to do the same job. Once we have solved a path for our robot, all the inverse kinematics, we then need to synchronize all of our motors because they all run independently of each other. So the algorithm that we follow is we time all of the motors to do all of the motion. Then we find the slowest motor and sync all of the motors so they start and stop at the same time. We then determine the frequency at which to run the motor, and then we match all of the times together. This is how we create the VFD instructions for controlling our motors, our robot's motors. Once we have all of this data on how we control the robot, then we have to send it to the robot controller. We use the Teensy 4.1 for its incredible computing power. We communicate our VFD instructions from our microprocessor to our microcontroller using UART serial. We use 6 of the 32 onboard timers on the Teensy 4.1 to create 6 variable frequency 50% duty cycle signals. We store all of the data for a continuous move inside of the motion structure, and each point within the motion is described within the point structure. When a motion has been put together, we send the prerequisites. Once the microcontroller has received the data for the motion it needs to do, it stores the data, prepares for the motion. Once that is ready, it then stores the entire motion through a serial communication from the microprocessor. Then it awaits for an execution command from the main user. Once that is done, the robot then executes its motion. And when it is done, it then relays that back to the user saying the order has been complete. Now, to keep track of all the parts within our database system, we designed our own SQL database, where we're going to keep track of all of the features of each part within the storage area. Most notably, we keep track of the part ID and number, its location and physical dimensions on the shelving, also the current weight and the serviceability of that part. And we designed a very robust system, so anybody changing the functionality of our robot, they can easily manipulate all of it. We mimic a similar idea to how a GitHub repository works. we pull a local repository of all the parts within the system, manipulate all the parts, get all the data, do what we so need to, and once that data has been verified, we then store it long-term on a hard drive.
So the robotic system that we're using for our application is a 6 degree of freedom robotic arm. Each joint is being controlled with a stepper motor. Each stepper motor has its own internal gear reduction, but some of the joints, for example, the arm joint or the elbow joint, which needs high torque, they have their own additional external gear reduction as well. As my partner explained, we control the speed of the motors using a VFD, which is a variable frequency drive. To control the speed, each motor will run with a certain frequency at a certain time to travel a certain distance. The robot is designed in a way that each motor has an angular velocity of half pi rad per second and an angular acceleration of pi per rad per second squared. Now you might be wondering how we manipulate all the beans around. So to do that, we designed a forklift system for our end effector. The fork is 20 centimeters long. From one side, it will be screwed to the robot's end effector, and from the other side, we have those two little keys that will keep the bin in its place and make sure that the bin won't slide out when the robot is moving around. The fork is so strong it can tolerate up to 4 kilograms of load without being permanently damaged or deformed. Based on the design of our fork, we designed a bean holder. The bean holder has a very unique design, and it's very simple to work with it. All we have to do is to just put it in like this, and it's secure. Once it's in its place, the slots in the front, side, and at the back will make sure that the bin is secured and won't move when someone is moving it around. Those four little rectangular holes at the bottom are designed so the fork can easily slide in and move the part around. Then the robot's workstation can be described in two parts. The first is the shelf. So the two bottom floor of the shelf is being used to connect the robot's pedestal to the shelf, so everything becomes one unit. And the two top floors of the shelf is for storing the parts. Each floor can tolerate up to 20 kilograms of load without being breaking down. The robot's pedestal is where we're going to mount the robot, and it has these four little diagonally cut aluminum extrusions, which are being used as the robot's resting position. So when the robot is not being used, it will rest in that place. So after putting together all of those mechanical things, we will get a system that will look like that.
So once all of these systems come together, we integrate them, we're able to create something of this motion. Great. So some of the key recommendations that we have for some of the key recommendations that we have for our system moving forward is a linear rail system, a scale feedback for understanding the stock within our system, a security key fob system, and we have certain mechanical modifications that we would like to make moving forward.
So one of the features that we can add to our system that will make it more efficient is the linear rail system. We believe that it's beneficial for several reasons. First, safety. So by adding this, we will make sure that the user-defined area and the robot's working zone is separated. It also will increases the order capacity from one part per order to 6 parts per order. And it will also give the robot the ability to keep track of resources and deliveries.
Now, we never fully realized the scale within our system due to time constraints. It was designed to be able to weigh up to 20 kilograms per order, and it would relay the relative weight change of an order to determine which part was added and removed and how much it weighed. This way we could track it. Due to the distance that the scale would have to be from the main robot controller, common communication protocols like serial, UART, I2C and SPI would be inadequate at the distance due to a very noisy environment. So we designed it to use the CAN bus communication protocol. The key features, the key reasons why we chose CAN bus is it has CRC error handling within itself, and instead of using a data addressable, it uses a priority message-based system. So all devices can talk at the same time, but who gets to talk is determined by who has the highest priority within their address.
So there are some mechanical modifications that we believe is going to be useful for our robotic system. One of them is brakes. So by adding brakes to the motors, we can make sure that in case of an emergency, we can properly shut down the robot. Also, we believe that by adding a worm gearbox to some of the high-low joints, we are able to reduce the backlash and prevent the back drivability of the motors, which recently caused some problems for us.
And one of the final functionalities we would want to add to this is a key fob system. This would allow dedicated users at Edison Motors to have priority in who gets to use the machine. This would come at 3 levels: a general operations level. This would allow technicians to go get parts when they need it and how they need it. The second level would be maintenance and operations. This would allow someone who has security access to change the robot's functionality or do maintenance. And the highest level being the production manager. They'd be able to scan their key card, decide what data they would like, and email to them for further analysis when they're shopping. And this is our capstone project.
Well done, boys.
Questions, comments, concerns? Yes.
You said VFD instructed. Do you actually have a VFD in your system?
No, we kind of ran into some terminologies for that. More specifically, what we use is we use more in the sense of a PWM we use a PWM system, but instead of modulating the duty cycle of that PWM, we keep it fixed at 50%, and we change the frequency at which we send these pulses. When we did our own research, there's not a clear name of what it is, so we thought the closest thing would be VFD.
Frequency modulation. Yeah.
Thank you very much for that information. We will update that in our manual.
Please do, because VFD is a specific component. And
Okay. Thank you for the information. Yes.
What is the first two-part question? What is a worm gearbox? And secondly, how do you train those worms to change things?
So worm gearbox uses the idea of, imagine a standard gear, but instead of 2 gears rotating opposite each other, one of them is a cylinder, where instead of the teeth going around the circumference, it is going around the surface volume of the gear itself. So instead of rotating like this, in the sense, it's a circular tube spinning. By putting a standard gear on top of that, as this rotates with it, this spins, and we would take the output of that. Worm gears are next to impossible to backdrive without breaking it, and they have really low backlash. Backlash meaning how much you can move the robot, how much you can move the joints without actually moving the robot. It's like the slop in the system.
Thank you. Any other questions?